We've landed now on the EUSAVE Heating System page. Let's take a look at what it has to offer us. Based on what we entered in the fuel usage, we've defined some heating systems already. The tool has calculated our energy cost per year, business as usual annual cost, our business as usual lifetime cost, and recall that our lifetime was set at 20 years, and this includes the energy escalation rate that we input as well. EUSAVE has also calculated the annual BTU load and BTU consumption. The difference between these two numbers represents the efficiency losses of the heating system. If we slide over here, we can see that the combined efficiency of our heating systems is 81.4%. The tool breaks out electric heating consumption, fossil heating consumption, and renewable energy consumption. Renewable heating fuels would include pellets and cordwood. The adjusted price per million BTUs. Heating system efficiency is the average weighted efficiency of each modeled heating system. That means it accounts for the percentage of contribution each system has to the household heating energy and its efficiency. The average fuel price escalation has also been weighted depending on the contribution of each fuel. Our energy use in BTUs per square foot has been calculated, and our heating BTUs per heating degree day per square foot has also been calculated. You may find this a useful metric for comparing the energy use of homes in the same climate. And the heating load after our shell improvements has also been accounted for. It's important to understand that this number will not be meaningful until after we start assembling packages, and that comes a few steps later. So let's just ignore this for now. Next thing we want to do is dive into our current heating system and our proposed heating system and make sure that they are doing what we want to do for our future heating needs. The first thing I'll do is edit the scenario name. Instead of heating scenario 1, I can make this a more memorable name. I can choose which current heating systems to include in this scenario, and I'll include both of them. And this is in package 1. Save. You can see that the system name has now been edited to something more memorable. And now I'll explore the current heating systems. Based on what we entered earlier, we have fuel units for each fuel type, and we need to decide whether or not each system will be replaced. And if we're going to keep them, we want to be able to define the future use relative to the current use. So if we're going to cut each one down by half, we can edit those down so that they contribute 50% of the load compared to the proposed system. And you can see that we have additional numbers for each heating system, and these figures will fill in later once we define what we want to do with each system. Let's start with our electric heating system. We'll edit this. You can see that it's in our heating scenario named switch to heat pump. This is an existing system. It's an electric system, and the seasonal fuel units used. If I tell the tool to replace this heating system, it will delete it. If I choose don't replace, then I need to decide what the future contribution percentage will be relative to the existing contribution. So for example, if I think I'm going to cut down my electric heat use by half because I'm adding a heat pump, I would take 2575 divided by 2, and that would be my new electric kilowatt hours for future heating use. So if that's the case, I will say 50% relative contribution and save this. I'll do the same thing now for my gas heat. I expect that my gas heat is going to drop dramatically, and I will not replace it. I'm going to keep it because I live in a cold climate. I want to ensure that I get enough heat during the very coldest part of the winter. So I will say that this is going to be used about 20% of the time. Save that. You can see the numbers have populated now. I'm expecting to use about half the electric that I used to and about 20% of the gas that I used to use. And over here, the tool has calculated the current load contribution, the future load contribution, the future seasonal fuel units based on those contribution percentages, and the future load percent after our shell improvements have been done. Again, these numbers will not be meaningful until after we've built a package which comes just a few modules down the road. So again, we'll need to ignore that. Now we can close these and open up our proposed heating system. Nothing's been proposed. We have to add a heating system, and we're going to add a new heating system to scenario named switch to heat pump. It is a proposed heating system. It's going to be an electric air source heat pump with an efficiency or a coefficient of performance of 250%. I think I can install this for about $4,500 in this project, and the incremental maintenance cost compared to my existing systems I'm going to leave as 0. Now you can see that the tool has calculated and filled out all of the numbers that we've told it to enter. Replacement load percent of 100% assumes that the heat pump will pick up 100% of the remaining load that we've defined here. So we've got future load contribution of 18% and 4% for each of these fuels, but 100% of the remainder, in other words 100 minus 18% minus 4% equals 78%. So in reality, our 100% remaining contribution of the electric heat pump represents a total of 78% of the heating contribution to our home throughout the season. We estimate about 11,987 kilowatt hours will be used. We've got our load, consumption, and again consumption after shell improvements, which will only be useful once we have a package built. Now I'll close these just for clarity. Let's just take a look at the evaluation totals for switching to our heat pump. We've got a cost to buy and install, maintenance cost, proposed energy cost. Now this is all three of those systems combined, both electric systems and the gas system. Proposed lifetime energy costs, our annual savings, lifetime savings, the cost to own and operate all of those systems annually and lifetime, our annual energy savings, lifetime energy savings, electricity consumption, fossil fuel consumption, and renewable energy consumption. The lifetime value of this heating scenario is $1,992. That means that over 20 years we'll have saved $1,992 when we add up all of the energy costs, all of the costs to install and maintain the systems, minus the energy savings of those new systems. Our simple payback has come in at 13.8 years. We have a fairly low return on investment and a benefit cost ratio greater than 1, which is always a good thing. Improvement cost per million BTUs saved. This is a fairly inexpensive system to install in terms of how many millions of BTUs we're going to save. However, in terms of carbon, we come out negative because the carbon intensity of electricity is much greater than that of propane. Now, if I wanted to explore additional heating scenarios, let's say for example I wanted to remove all of my heating systems and install a single high efficiency gas boiler, you could model that scenario as well and then compare your system evaluation figures and see which one you and your customer like the best. We're now done with modeling our heating systems, so let's move on.